Okay, in this video we're going to look at differentiating these circular functions, but just before we get onto that, I wanted to sort of highlight this quote that I've got up here, which is, "The only way to learn mathematics is to do mathematics," which I really like because it kind of sort of puts it simply, which is to say that you need to practice to be able to do it. And practice involves getting it wrong, so you need to be happy to jump in there and give it a go. Don't be afraid to get it wrong, because that's the way you learn. So that's your little inspirational thought for today. Right, so let's look at differentiating sine, cos and tan. So just to have a look at the way syllabus requirements, this is really important because this tells you what you legally can and cannot be examined on, particularly obviously in year 12 looking at your ATAR at the end of the year. So the syllabus requirements say that you need to be established derivatives of sine, cos and tan graphically with numerical estimation or in formal proofs. Okay, so that's the content descriptor 3.1.5 if you want to go and have a look at it. So the proof that's done in the book, in the Cambridge text, is really rigorous. Mathematically, it's absolutely correct, but it's probably not strictly necessary. If you can work out the derivatives from a graphical point of view, which I'll show you, or doing numerical estimation, which is sort of your limiting chord, but with technology, then you'll be pretty much right. So yeah, Cambridge can sometimes be a little bit over-enthusiastic in its approach, so don't get too concerned if you're finding that the math there is going over your head a little bit. Okay, just a warning before we dive in, these rules only apply when the angle is measured in radians. Okay, we're leaving degrees behind now, we don't deal with degrees all that much, certainly not when we're talking about circular functions once we're in upper school, so make sure that everything you do now you're thinking in radians. So switch your calculator, your class pad into radians, and also your brain. Okay, so let's have a look at the sine curve. So the sine curve is this blue one, which you'd all be intimately familiar with. Okay, we're measuring in radians, so this is our pi, 3.14, and 2 pi over here. Okay, now we know pi and 2 pi. We know that the derivative is the gradient, okay? So if we look at the point here as 0, the gradient at that point, at that exact point, is 1. So that's where this lines up with 1 here. Okay, but as we come up, the gradient it's getting less and less steep until it comes up to here where we've got a stationary point. So the gradient is 0, stationary point. And you can see that that lines up nicely with gradient 0 there. Okay, now we're into a negative gradient. So this is why this curve is negative. Negative gradient coming down to 1 here as well. So this is negative 1 at this point. So the gradient there is negative 1. And that lines up with negative 1 down here. Okay, and then coming down, continuing down, we get here and we've got another stationary point. Stationary point there, and that lines up with that 0 there. So this is the function that we're interested in, and this is the derivative, or the function of the gradient. Now you should be looking at that going, well, that looks familiar, because of course that is the cos function. Starting at 1, coming down to a minimum of -1 at pi, and then coming back up to positive 1 here. So we can see just by examining the gradient that the derivative of sine x is cos x. Okay, so if you have f of x is sine x, then f prime of x, the derivative, is cos x. Okay, so that is your rule. The only thing is we throw in this little constant here if you've got a dilation going on in the brackets there, then you need to bring that out. Okay, so you have f prime, so if f of theta is sine k theta, then f prime theta is the derivative of what's in here. Okay, so in this case it's k, derivative with respect to theta, k cos k theta. Okay, so it's really pretty straightforward. Here's the example to demonstrate just how straightforward it is. Alright, so we've got y equals sine 2 theta. We want to find the derivative, dy dx, or dy d theta actually, to be exact. Okay, the derivative of that is 2 cos 2 theta. Okay, so very straightforward. Just differentiate what's in the brackets with respect to the variable, put that out the front, change sine to cos, and away you go. Right, now this one's a little bit different. We're going to have to do a chain rule on this one as well. Okay, so we're saying that f of x is sine squared 2 theta. So if we let u equals sine 2 theta, then what we have over here, this is u squared. Okay, so remembering f prime of x is just going to be 2u, and differentiating this is going to be 2 cos 2 theta. Okay, and of course then we multiply those together, so f prime of x is 2u, so it's like dy dx, so dy du times du dx, so 2u times this derivative, 2 cos 2 theta. Okay, so that gives you 4u times cos 2 theta, and then going back to what u was sine 2 theta, so you've got 4 sine 2 theta cos 2 theta. Okay, so again what you're finding is we're starting to mix up some of our rules, so using the chain rule and getting sort of involved with all the different tools that you've now got in your toolbox. Okay, so for doing cosine, it's exactly the same approach. So we look graphically. The blue curve is the cos curve, which we're very familiar with, starting at 1, coming down to -1, going back up to 1. Okay, if we take the same approach, at this point the gradient is 0, so that's 0 gradient here. Coming down, we've got -1, so that's -1 at this point. Okay, -1 gradient. Down here, we've got another stationary point. Stationary points, so these are our stationary points. Okay, and you can see they're lining up with the zeros there. There's another one over here. This stationary point. Okay. And as we graph that, then we can see we've got the sine curve, but it's not actually the sine curve, it's a reflection of the sine curve about the, well, either way, really, about the x or y axis. So it's negative sine x. Okay, so instead of going up and down, as it usually does, it starts off going down and up. Okay, so what we've then got is if f of x is cos x, then f prime of x is negative sine x. Okay, and same thing applies with if you've got a constant in the brackets there. Just differentiate that, bring that up front, minus k sine k theta in this case. So you'll often find that we talk about theta instead of x. Sort of depends, doesn't really matter which one you use, but often for angles we use theta. Okay, let's have a look at a couple of examples. So this one, again, it's a chain rule. Okay, because we're going to say let u equal cos 4 theta plus 1. So then f of x is going to be u cubed. Okay, so f prime of x is going to be the derivative of this times the derivative of that. Okay, so the derivative of that is just going to be negative 4 sine 4 theta plus 1. Okay, the derivative of that is 3 u squared times this one, u prime, minus 4 sine 4 theta plus 1. Okay, multiply that out, you get your negative 12 at the front. Okay, remembering that u was this, so we can, instead of writing u squared, we can write cos squared 4 theta plus 1. Okay, so that takes care of that bit, and this minus 4, and then times sine 4 theta plus 1. Okay, and that's your answer for that one. Alright, this one's slightly more involved, so now we're looking at y-coordinates and gradients of tangent. So gradient of tangent, remember if you see this, gradient of the tangent, that means differentiate. Okay, that's what it's asking you to do. So for this one we've got y equals cos theta, and we're looking at the points pi on 4 and pi on 2. Okay, so let's have a look first at when theta is pi on 4. Okay, so that means y is going to be cos pi on 4. And of course cos pi on 4 is just 1 over root 2. Okay, and y prime, if we differentiate that, it's negative sine theta. Okay, and that will be negative 1 over root 2. Okay, so this is your y-coordinate over here. Y-coord, and this is your gradient. Now we can do the same thing for theta equals pi on 2. Okay, so y is cos pi on 2, which is 0. Okay, and y prime negative sine pi on 2, which gives you negative 1. So again, y-coordinate and gradient. Okay, so pretty straightforward there, just sort of extracting the required information from the question. Also remembering that you need to be fluent with your exact values. This is definitely a calc-free kind of question. Okay, now tangent always likes to be a little bit different. So when we have a look at this, you'll see it doesn't look the same as our sine and cos curves. Yeah, obviously we've got these asymptotes, we've got an ever-increasing gradient up to the point, well, basically an infinite gradient. So when you're trying to plot the gradient on the same curve as tan, you can see that we've got a very, very steep gradient all the way up here. It's getting less and less steep. It's always positive. So it's always a positive gradient, always sloping up, but it's getting less and less steep until it gets to this point where this is your point of inflection. Okay, so that's where it changes from concave down to concave up. That's the point of least gradient. Okay, and at this point on tan x, it's 1. So that's there, so the gradient there is 1. Equals 1. Okay, and then it shoots off again, starts getting steeper and steeper and steeper. And then clearly with the periodicity, it just repeats each time. Okay, now that's a funny looking kind of function. We haven't really seen one of those before. Okay, but if we come across something called sec or secant, sec is short for secant. Okay, secant is defined as 1 on cos. So we say 1 on cos theta is sec theta. Okay, and if you plot that, you get this funny looking graph here. Alright, which doesn't quite look like what we had. If you go back, this was all positive, but it's kind of the same shape. Okay, the way we can sort of fix that is by squaring it, because obviously if you square it, then all your values are going to be positive. So if we square this, so we have 1 on cos squared theta is sec squared theta, then we get all positive values. Now that looks like what we had when we were plotting a gradient on the tangent curve. Okay, so the rule there is that if you've got f of theta is tan k theta, then the derivative is going to be k sec squared, don't forget the squared, k sec squared k theta. Just a little disclaimer, you don't actually need to know this. Tan is not on the course, but you know, if you're doing sine and cos, you might as well do tan. It's fun, okay? We do calculus for the fun of it. Alright, so quick one here. You've got y is tan 3 theta. Okay, if you want to differentiate it, 3 sec squared 3 theta. Okay, really straightforward, and you won't be asked to do any of that on an exam. You just need to make sure that you're sort of comfortable with it. And it's good in the book because they do sort of mix up your sine, cos, and tan. So being able to do that is a good thing. So there are 3 rules to remember. If you've got y is sine x, the derivative is cos x. If you've got y is cos x, the derivative is negative sine x, don't forget. If you've got y is tan x, then the derivative is sec squared x. And remembering if you've got a k in here, then that just comes out the front and stays here as well. Keep in mind that the derivative is the gradient, okay? I find this really useful if you do have a brain freeze. You suddenly think, oh my goodness, is it positive or negative? Cos, when you're doing sine, you can draw a quick sine curve and think, okay, well the gradient there is 1, the gradient here is 0, the gradient here is 1, negative 1, the gradient here is 0, right, that's cos. Okay, so you can sort of plot that and make sure that you can think your way out of any kind of brain freeze that you get in an exam.